Hi, good morning. Can you hear me? Good. Okay, so let us wait for 2 3 minutes and then we will start. So, can you see my screen? Good. So, some of your friends have requested to do a quick recap for last class. So, I will try to do a very quick 5 minutes uh, summary of the last class that we what did we cover. So, we in the last class we covered the different aspects of DFA. And today we will start with the concept of NFA, deterministic and non-deterministic finite automata. Deterministic, the basic difference between deterministic and non-deterministic finite automata is that when we are talking about deterministic finite automata DFA, then at every state, for every symbol, the output state is well defined always. So whenever the machine is in the process of computation, one by one the symbol are being fed and the state is being transitioned from one state to another. So at any point of time, at whatever state the machine is, given any input symbol, we always know what the output state is. That is a unique state on the that will be the transition when at the current state the machine is fed by a symbol. So that is why it is called a deterministic finite automata, 100% predetermined. But non-deterministic finite automata means that it is a there is a concept of chance. There is a concept of multiple states coexisting, coexistence of multiple state at any point of time. So you cannot determine 100% at which state, at which particular state the machine is at any point of time. It may be that there are n number of states and the machine can be at any one of those states at any point of time, or other way of saying it is that it is at all the states at that point of time. So this is a very simple trivial example to show the difference between DFA and NFA. Here you can see that from S1, when we give 0 in the deterministic case, the output is S2. So when the machine is at state S1 at any point of time, you feed with the symbol 0 and the output is S2. Whereas in the non-deterministic case, you can see that there is a 0 comma 1 here and a 0 here, which means that when the machine is at state S1, then you are feeding, if you are feeding it a symbol 0, then either it can go to S2 or it can go to S3. So after S1, on seeing 0, the machine belongs to either S2 or S3. So the output of the transition is not a unique state but a set of states. So that is the basic difference between a DFA and an NFA. We will look at the different aspects of NFA, but before that, let us try to define that how we compute an acceptance of a string by a DFA. How do we compute that? And to do that, we need to define this extended transition function, which is denoted by delta hat. This extended transition function denotes is the tool using which we compute the acceptance. Let us see how do we do that. Before that, let us try to design a DFA. Let us try to design a DFA. So we are trying to design a machine which will accept both even number of zeros and ones. That means any string of zeros and ones which will contain even number of zeros and even number of ones in any order. The order does not matter. So that's a machine that we are trying to design, and this is the machine. This is the machine that does so. You can see that Q0, which is the start state, which is the end state or final state as well. So this means that empty language, that is epsilon, is also accepted by this machine, because by definition it should contain even number of zeros and ones, and an epsilon contains zero number of zeros and zero number of ones, and zero is an even number. So empty string is also accepted. So the start state is the final state, and this is the machine. And how did we design? How did we decide that there are four states that you can get from this? That you should be able to get from this notes, right? So I'm not reiterating all this stuff, but this is how we compute the acceptance automatically, step by step. That means you can write a program. You can write a program to compute the acceptance or rejection of a string by a machine. So the program is fed into the initial parameter is this table, is this transition function, which defines what are the number of states q0, q1, q2, q3, what are the input symbols 0 and 1, and at each step given an input what will be the output. So then the machine does this delta hat q naught 1 is q1, because we can see q naught 1 q1, then q naught 1 1. That means we are applying delta on delta hat of q1, q0 and 1. Then 1 1 0 means we are applying delta on delta hat of q naught 1 1. So it goes on like this, and using this transition extended transition function, you should be able to compute the acceptance of a string or the rejection of a string by a machine. And this gives you the hint of how you can write a program, right? So this is and regular language, as I told you earlier, that regular language means that it's a language which is accepted by a machine, so that you can design a machine which accepts that particular language, right? So that is this is a machine which we are trying to prove that AWA, where W is any string of A or B, W belongs to AB star. That means W is any string contains any number of A's and B's. So we are trying to prove that this L is a regular language, and to prove that you should be able to design a machine. You should be able to design a machine, and this is the machine which contains three states: Q naught, Q1, and Q2, and it takes a and a, and then the in between W is like this: B star and A star here. But if the input starts with B, if the input starts with B, then definitely it is not accepted. So this Q3 here, you cannot come out. The machine cannot come out of this state Q3 if the input starts with B. And after A, if I give lots of B and then A, then it is accepted. But again, if I give a B, it comes back here. So the final state always coming from different states with a A. So the final alphabet war symbol, the final symbol is A. The first symbol is A, and in between you can have any number of A's and B's. So this is a machine which accepts this language. So this language is a regular language, right? And this is the transition function. These are the start state and final state. So with this, I gave some exercises. I don't know whether you got some time to work on these or not. I didn't get any feedback from any one of you. You can send me WhatsApp messages also. If you could, definitely you could solve these problems. If you want, you can send me WhatsApp messages. I can just look at those solutions and can point out uh, whether there is any defect in your solution or not. You can do that. Okay. So now we are going into non-deterministic finite automata. This is new. So far we have seen that at every step of a computation, the machine is in a given state and reads the next input symbol and transitions to the next state, which is uniquely determined. But a non-deterministic machine, several choices may exist for the next step at any point. Right? That's what I said. So non-determinism is a generalization of determinism. So NFA is a generalization of DFA. So DFA is a special case. NFA is a more generic case where the output might be a set of states, and DFA is a special case where the output is a particular state. So every DFA is automatically a NFA also. Every DFA is automatically a NFA also. Now, some key points. An NFA has the power to be in several states simultaneously. I have already said that. That means after a transition, there may be there's a possibility that the machine uh, can be either in state this or in state either in state A or in state B, something like that. Every NFA accepts a language that is also accepted by a DFA. That means if a language is accepted by a DFA, or other other way around, the language accepted by an NFA, you can design a DFA which also accepts that particular language. So you design an NFA, you compute the language which is accepted by that NFA, then you should be able to design a DFA which also accepts that particular language. That means for every NFA there exists a DFA. For every NFA there exists a DFA, and NFAs also accept only regular language, because since if for every NFA there is a DFA and DFAs only accept regular languages, so NFAs are also only accepting regular languages. So why do we need an NFA? We will see. We will see in some future. I mean, next class probably, that designing an NFA to solve a problem is much more easier compared to designing a DFA. NFAs are more NFAs are closer to the higher level languages, and DFAs are closer to the low level languages. So we generally, what do we do? We generally design a NFA and then we convert the NFA to a DFA using some tools and techniques that we will discuss. An NFA can always be converted to a DFA accepting the same language. So there is a specific process using which you can convert a NFA to a DFA. The corresponding DFA might have lots of more states compared to the NFA. So the corresponding DFA will have, might have, but in most of the cases will have more number of states compared to the NFA. So in an NFA, if it contains n number of states, then in most cases the corresponding DFA will contain larger than n number of states. And in the worst case, it will be 2 to the power n. In the worst case, it will be 2 to the power n. Why this is so? Because that you will understand when we will see the conversion logic. How do we convert? Because every possible subset of the set of states. So if the set of states has got only n states, then the number of possible subsets of that set is 2 to the power n. So in the worst case, all those 2 to the power n subsets might be a valid state in the DFA. So for n state near NFA, the worst case DFA will contain 2 to the power n. So now you can imagine the complexity of the DFA, right? So let us see a NFA here. It looks pretty simple. A NFA accepting all strings ending with 0, 1. So it's a string of 0, 1, alphabet is 0, 1, and you are designing a machine which ends with 0, 1, right? So you are designing a machine which accepts any string that ends with 0, 1. So now this machine, how does it accept this kind of strings? Because you can see that first of all there is a non-determinism here. From Q0, if the input is 0, then there is a possibility that the machine either stays in Q0 or moves on to Q1. So there is a non-determinism that is inherent in the characteristic of this machine. So this is, first of all, this is a NFA. Now, how do we how do we guess that this machine takes this kind of strings? Because you see that initially, let us assume that the string that we are feeding with is 4 zeros, 0, 0, 0, 0, then 0, 1. So 5 zeros followed by a 1. Say for example, this is a string. So if you are looking at this NFA, then how we will do the acceptance? Because the first 4 zeros, it will remain in Q0. Then on the fifth zero, it moves on to Q1, and then the final one, and it goes to Q2. So it lands up in the final state, which is an acceptable state. So this tree is accepted. Now, the thing is, how do you know that after the fourth zero, on the fifth zero, you have to do this transition? You don't know. The machine doesn't know how many digits, how many symbols will come. It only can see the current symbol. It can see only the current symbol, that is zero, nothing else. So it can guess. What it can do, it can guess that probably it is the zero of the terminating zero one, but it might not be. So that is why it keeps both the tracks open. It might be a zero of the terminating zero one, or it might be a zero of the initial mass of zeros and ones. So that is why you have the possibility of two different states. On seeing a zero, the machine moves to either Q0 or Q1, both. So this is a example of a very simple uh, non-deterministic finite automata. Now let us see some highlights. State Q0 may transition to itself on seeing 0 or 1. However, it may guess on seeing a 0 that it might be the 0 of the terminating 0 1. So there are two options for the automaton when at state Q0 and input given is 0 to either transition to Q0 or to Q1. To be precise, it transitions to both. So that means it now the current state after Q0, if you feed the machine with a 0, then the state of the machine is both Q0 and Q1. We will see. We will see with a very good pictorial example, pictorial way we can depict. Now there are some more points that needs to be noted. I am reiterating these things. I am repeating these things again and again because these are some basic fundamental things which needs to be which needs to go very deep into your mind to understand the next few concepts. So no transition from Q1 on input 0. You can see that if you look at this LFA, there is no arrow going out of Q1 labeling 0. We have not seen this in the case of DFA. In the case of DFA, at every state, there are arrows coming out labeled with all the input symbols. It should be determined at every state that on any symbol what will be the output state. But here you have the liberty to leave that. That means that is undefined. At Q1, if you see an input 0, then it is not defined. So we assume that the output is an empty set. There is no transition happening. So it is an empty set. Likewise, at Q2, no arrows are coming out. So at Q2, if you give it a 0 or a 1, no transitions happening. So it's an empty set. It's dead. The machine is dead. You can say that the machine hangs. It's not accepting any input at Q2. It hangs. Right? So now let us see a pictorial way of computing the acceptance. So the machine at the very beginning it is at Q0. We know all that this is the start state. Now the first symbol which is fed is 0. So after 0, what are the output states? You can see that it is either Q0 or Q1. Q0, Q1, both. After Q0, on seeing 0, output is either Q0 or Q1. Now, then you are feeding another 0. What happens? At Q1, 0, it is stuck. So this branch of the tree ends here. If you would have fed a 1, then there would have been a transition from Q1 to Q2. But since you have fed the 0, so this branch ends here. It's dead. But another branch, it is going on because you another state was Q0, and from Q0 on seeing 0 it again forks to either Q0 or Q1. So now these two branches are alive. Now you are feeding a 1. So from Q0 on a 1 it moves on to Q0, right here. Q0 a 1 Q0, and from Q1 a 1 means Q2. So after this one, the possible states are Q0 and Q2, and both the branches are alive. Now you feed another 0. At Q2, you are feeding a 0, it's dead. Because at Q2 there is nothing defined. So this is end here. This is the end of this branch. But this again forks two branches from Q0 on 0, it is Q0 or Q1. And then a 1 again, so Q0 and Q2. So these are the two states, or the final set of state is Q0 and Q2 after 00101. Now since Q2 belongs to this set and it is a final state, so this means that this string is accepted. So after a string is fed to a NFA, the set of states which comes out, if one or more final states belong to that set, then we say that the string is accepted. But there is a possibility that this branch ends up, after looking at 00101, there is a branch which goes to a final state, right? Okay, so now let us quickly look into some more facts of NFA. The definition of NFA and DFA are identical except the transition function delta. And how it is different? Delta is defined as a function that takes a state and a symbol as input as usual, like DFA, but returns a subset of Q as output. So the output of the return of this function delta is not a state like DFA, but a set of states, which is definitely a subset of Q. Q is the set of all states. So it returns a subset of Q as output. So that is the basic difference between the delta of a DFA and delta of an NFA. Right? So the difference is that the transition function returns a state where for DFA, whereas for an NFA it returns a set of states. So now if we look into this NFA once again, how does the transition function look like? The formal definition is absolutely similar to the formal definition of DFA, which contains 5 tuple. One is the set of states Q, one is the set of symbols, that is the alphabet sigma, one is a transition function delta, one is a start state, and one is a set of final states. So this is similar, but the behavior of this delta is different and it looks like this. So as usual, you have your states here with the start state as an indicated by an arrow and the final state indicated by a star, and the columns contain the symbols 0 and 1. And on seeing Q0, on seeing 0 at Q0, the output is a set Q0 comma Q1. So this is the difference. So the elements here for a DFA, the elements here are states, but here the elements here are set of states. And another difference is that it may contain this empty sets file, whereas in DFA you cannot have file. It should be a state. So this is the transition function on Q0. On 0 you have Q0 Q1, Q0 1 it is Q0, Q1 0 it is 5, Q1 1 it is set Q2, and on Q2 it is both 0 and 1 empty 5. So this is the transition function for this NFA. Now how do we compute the acceptance step by step? Let us see the steps to compute the acceptance of the string 00101. 00101 we have seen pictorially. Now let us see computationally how you can write a program, a computer, without having a knowledge of this graphical arrow and all that stuff. Just looking at the table, just looking at the transition table, how does it compute whether a string is accepted or rejected by that machine? So this is our transition function, and delta hat q naught 0, the first symbol being fed is 0, and it gives me a, it returns q0 and q1, a set. Then this, I feed this delta hat, then I feed a delta of 0. Delta hat q000 is, delta hat q00 was q0 q1, so I feed a 0 on this q0 and I feed a 0 on this q1. So now this becomes a union of delta hat q00 and delta hat q10. If you don't understand or if there is any confusion in your mind, you can ask. You can ask questions at any point of time. Now, delta hat q00 union delta hat q10. So delta hat q00 is q0 q1 and delta hat q10 is 5. So q0 q1 union 5, that is q0 q1. Now I will feed a 1 here, 001. So I will compute delta hat q01 union delta hat q11, right? That's what I will do. Q01 union q11. Q01 is q1 and q11 is q2. So it is q0 comma q2, right? Now 0010, which means q0 q2 I feed a 0, so q00 and q20, which gives me q0 q1 union 5, that is q0 q1, and finally another one, so q01 union q11, that is q0 q2. Now q2 is a final, q2 is one of the final states, so I see that q from delta hat q0 I give 00101. My final set of states is q0 comma q2, and q2 being a final state, we say that this delta hat, this transition function, it accepts this string 00101, right? So that is how we compute the acceptance. Now, if I again see the picture that we discussed in the last slide, in the previous slide, now you can find an analogy. You see, after Q0, you give 0, and your possible states are Q0, Q1, Q0, Q1. Then after 0, 0, after 0, 0, it is Q0, Q1. I'm sorry. So, Q0, Q1. After 0, 0, 1, you see it is Q0, Q2. After 001, it is Q0, Q2. So 0010, it is again Q0, Q1, 0010, Q0, Q1, and 00101, it is Q0, Q2. 00101, it is Q0, Q2. So this is actually the computation of the acceptance, but this one we see the machine and we compute, whereas this one we see this transition table and we compute. So this is the blind computation. This can be implemented by a program very easily. This can be implemented by a program very easily. So this is the computation of the acceptance of an NFA. Now this is a simple comparison, a deterministic computation. It starts, and then after each symbol it goes to a state. This state is uniquely defined, so it is kind of this. And finally it lands up at one state, and this state can be either accept or reject, depending on whether that state is a final state or not. Whereas for a non-deterministic computation, it goes on like a tree. Say from the start, on seeing a symbol, it forks to two possible states. Then the next input, this state can fork into three states. This state can fork into two states, and probably this it ends here. This ends here. This state, this branch goes on. This branch goes on, and like this one branch that leads to the accept. All other are rejection domain. But this one is accept, the final after the final symbol. So we say that this string is accepted. So this non-deterministic computation is more like a tree, whereas the deterministic computation is more like a point-to-point straight line. So this is a sample computation. This is not a computation by the NFA that I showed you earlier. This is just a sample computation. I just wanted to give you a just a feel of how you can compute using a tree, or how you can show the computation using a tree. So from Q1, seeing the symbol 0, I will include the corresponding NFA also in the slide so that you should be able to relate. Then a 1, so it goes on to Q1, Q2, or Q3. Then a 0, Q1 goes to Q1, Q2 goes to Q3. Then again a 1, Q1 goes to Q1, Q2, Q3. Q3 goes to Q4. So it goes on like this, the tree. And finally you can see that the possibility of the final set of state is Q1, Q3, and Q4. This Q4 might be might be achieved through different branches also. That does not matter. But the final set of states is Q1, Q3, Q4, and Q4 is one of the final states. So I will give you some. I will give you some example exercises where I will expect you to draw this kind of tree, the computation tree for the computation of on a string by an NFA. Right. So now we will stop here today. We will go to the equivalent DFA construction in our next class, that is tomorrow. We will see how we can construct the equivalent DFA of an NFA. For today it's up to this. Prakriti, are you there in the class? Hello. I'm sorry, Kritika. Yes, I'm extremely sorry. Kritika is the seer. Yeah, Kritika, are you in the class?
Yes,
Right. So, can you please record the attendance of today's class, and you record the attendance of tomorrow's class also, and then you send me this week's attendance after tomorrow.
okay, sir, I'm good.
Okay. Thank you, students. Bye.
कृतिका स्क्रीनशॉट लोगी क्या? कृतिका स्क्रीनशॉट लोगी क्या? अरे भाई, हम तो सिंपल सा क्वेश्चन पूछ रहे हैं, इसमें इग्नोर करने का क्या है? क्या खर्चा पानी लेके भाई?